Hello, today we will continue our lecture series in the topic of regression. And in our last class, we primarily focused on, we ended with the ideas behind subset selection. So essentially, we were talking about this problem where you have a lot of input variables in that you could use in your multiple regression model. How do you go about picking which ones should stay in the model and which ones should go out? And in discussing that, we were discussing a more broader topic, which is how do we measure how good a model is, and how do we do things in our regression practice so that we get good predictive accuracy and it's also useful for interpretation. In that regard, we will continue our lecture today and talk about two other small measures, which is the R square and the adjusted R square. The R square has at least been introduced to you, and you have an idea of where you can find that in your analysis. We'll talk a little bit about that, and we'll talk about them more as other metrics of measuring how good a regression is. And then we will move on to this topic called regularization, which has to do with how do you fine-tune the betas, the coefficients of your regression model. When we were discussing the topic of subset selection, which is how do you go about choosing which variable should stay in the model, we said we would go about making those choices based off of some metric, not of the individual variables but of the model as a whole. Correct? And in that context, we primarily discussed the use of the p-value from the f-test that you do with your ANOVA. So for instance, I have copy pasted the same results from our example that we took in our last class, and so this table out here kind of is just a copy paste from the previous Excel sheet, and we were focusing on this p-value primarily, saying this ANOVA is essentially a measure of how good the overall regression is, not individual input variables. But can we use this p-value as a guide to see which variables stay in and which variables stay out? And that is a context in which we discussed the topic of best subset regression. We spoke about backwards, forwards, and hybrid stepwise regression. But today what we're going to talk about two other measures which are also available and which is something that you could use. And they're primarily the R square and adjusted R square. So the first thing that we're going to start by saying is the R square is not a very good measure in terms of how the overall regression model is, especially in a multiple regression context. And I'll explain that in a second. What we mean by, again, just as a reminder, simple regression just means there's one input variable. Multiple regression means there are multiple input variables. So the R square essentially is a measure of how much of your variation, and here you're talking about variation in terms of y, your output variable. So how much of your output variables variation, there's some amount of variation, and how much of that can I explain using my model, and how much of that can I not explain using my model. So if I take the overall variation of y and I break it up into two chunks, the amount that can be explained by my model, which is my regression equation, and the amount that can not be explained by that, if I put those two together, I should get the overall variation in y, irrespective of x. So R square is nothing but this ratio of how much variation is explained by the model divided by the total variation. So depending on the software that you use and the textbook that you use, people usually have sum of squares total, and that's the total variation, and sum of squares model, that's the model variation. But I've also seen sum of squares regression as a proxy for sum of squares model, and the sum of squares, if you say the total variation is sum of squares total, and the model variation is either sum of squares model or the sum of squares regression, then the other quantity that is left is the sum of squares error, or as some people again call it, the residual sum of squares. You might have seen it as RSS or sum of squares error. Okay, So this your r square value therefore is nothing. You can just basically look at your ANOVA output, even if your r square for some reason disappears. It's nothing but the ratio of this number to this number, in which case I think that looks like it's about 0.8, 0.9 in value. To give you a little bit more mathematical intuition, I've also kind of given you some formulas that are used for calculating these three values. As I mentioned, the sum of squares total is just essentially the variability in some sense. This total squared distance of each data point from the grand mean, whereas sum of squares model is where you go to each not each data point, but here y of I is each data point, and you look at the deviation of each data point, actual data point, from the grand average. With sum of squares regression or sum of squares model, you look at each predicted value. Y I hat is nothing but what value of y are you predicting for each x, and look at the deviation of that from the grand mean. And finally, yi minus yi hat is how much is each data point deviating from each predicted value. So that should hopefully give you some intuition as to how these values are calculated. Okay, so now going back to a bigger topic, right? As a metric to see how good a regression model is, especially in a multiple regression where there are many variables, many input variables, this r square is not great, because r square by definition will only increase as you keep on adding more and more variables. So we will be discussing this in great detail in our lectures on the bias variance dichotomy, which is going to come up. But the core idea, just to kind of give you give you some feel for what we're talking about, is that if you keep on adding variables and if you can keep on adding complexity, right, at some point you should be able to explain away all the data that you have. Or in other words, take the example where you have 10 data points and you had only 10 data points. You should technically be able to fit a line, or essentially fit a function that will go through all these 10 data points if you just choose if you say I'm willing to fit a ninth order polynomial. Essentially, if the fitted model can get more and more and more complex, then for a finite set of data points you should be able to explain away everything. But that's not necessarily great, because when you go and try and predict with that model, you're not going to do too well. You've just kind of overfitted to the data by just constantly increasing the complexity of the model that you're using. Now, given that is the base, and given that we were talking about this idea loosely when we in our previous lecture spoke about how it's really important to try and figure out which of the subset of variables you want in the model, and you want to throw the others away. This r square does not help, because r square will never decrease as you keep on adding more input variables. So let's say I had a model with 5 input variables. I suddenly come up and say, maybe I should add the 6th variable and add it. It's definite that r square will increase. And so r square itself is not a great measure of how good a model is. Now, as we discussed, you could definitely use the p-value from the f-test of the ANOVA, but another metric that is also popular is called the adjusted r square, and that is essentially nothing but a modified version of r square that's shown in the formula here. So it uses, essentially to compute it, you can use your r square values, and the idea is that n is nothing but the number of data points, and k is the number of independent variables that are there. So for instance, in our example, right, I believe we had 88 data points in the Excel example that we were discussing yesterday. Yeah, it's 88. I can infer that also from the total degrees of freedom. And k essentially is 4, because we had 4 input variables. So you can use k, the k will be equal to 4. Okay, so 88 and 4. Okay. Um, the idea out here is that when you use the adjusted R square, it kind of penalizes models where the number of variables you're using to explain it is too high. So you can compare the adjusted R square of one model versus the other, where you've used different numbers of input variables. And yes, the higher your R square, the better it is. So if you can get a very high R square, you're going to get a, that's one way of getting a high adjusted R square, but not at the cost of, having too many variables. You want to keep k as small as possible, and have a very high R square. Notice that there's a minus in front of the k, but this whole thing also has a 1 minus. So just be careful when you're trying to get an intuition of how increasing or decreasing these values is going to affect the R square, adjusted R square. Okay, so that's more just again introducing you to the concept that it's not just the p-value of the f statistic as we discussed in the best subset selection and stepwise regression, but there's a concept of adjusted R square as well, and that's just one of them. There are other metrics also that can be used to measure a regression model. Okay, we now go on to the topic of regularization, and you can also use the term coefficients shrinkage to express the same concept. What regularization does is also has a huge overlap with what you try to do with subset selection, which is the core idea being, how can I simplify my model in some sense, because I care about predictive accuracy, I care about interpretation. I don't care about just trying to get this function to go through all my data points. So how can I simplify the model in some way? And one way of simplifying the model is to use fewer variables. That's what we saw in subset selection. But once you fix the number of variables, once you say I've fixed these are the variables that need to go in the model, is there some way to more smoothly determine the coefficients? We saw how the coefficients were being determined through an optimization process, but somewhere can I go directly in there and put in my constraint of saying, hey, I do want you to optimize something, but at the same time I want you to try and keep it as simple as possible without kind of overfitting the data. So in some sense, the problem of regularization is a problem of saying, I have an algorithm and I have a fixed number of input variables. So I'm no longer bargaining to throw variables out and keep them in. But is there some way of, in my fitting methodology itself, preventing this problem of overfitting, or preventing this problem of trying to get the functional form to be so hardwired to the data that it does not do such a good job of predicting, and kind of, can I impose penalties upon myself to kind of overfitting? One way in which overfitting happens is in problems of what we call as multicollinearity. Multicollinearity is the idea that many of my input variables are correlated with each other, and when you have that problem, the coefficients themselves through a regular regression process can get determining their betas can be kind of poor, meaning that there can be a lot of variance between one sample to the next. So it's like, ideally, if I'm doing a certain regression process, and I take a sample of data and then I do this regression fit, if I take another sample of data and I get a completely different set of betas, then that's not a very stable process. And that tends to happen with least squares regression when you have multicollinearity, meaning you have lots of highly correlated input variables. Take this example that we have on this slide, right? You have this idea where you get this equation which says y is equal to 4a plus 2b. Now, imagine a world in which a and b was so highly correlated to the point where they were practically the same variable. Then a fitted model that says y is equal to 10a minus 8b should also kind of give you the same results, in the sense that a and b are practically the same data points. They're correlated to 1, and now assume that they are also equal in magnitude. For a and 2b, you can substitute b with a and you're net getting 2a, right? which is the same net you're getting in the second equation. So are both equations the same? Now, the idea with something like ridge regression is in cases like this, you want to have the simplest possible equation, and you want to have the lowest possible magnitudes for your variables. So you would be very happy with a y is equal to 2a, and just keeping it as simple as that. Or you can think of it as 2a minus 0b. So in addition to choosing which variables, you want to keep their magnitudes, the magnitude of the coefficients, you want to keep them as low as possible. So if you have offsetting coefficients, you're not making a regression equation that says y is equal to 10,002a and a really large say 1002a minus 1000b, right? You're kind of blowing things out of proportion. It won't generalize very well, and so on and so forth. Okay, so how can we achieve this? How can we achieve this goal of in really simple terms, not just allowing highly correlated variables to take up opposing sides and have really large coefficients? And the way we would do that is by taking your standard least squares minimization problem, and that's essentially what I've written as the objective function here. So the objective function here is no different for the ridge regression. At least the way I've written it out here is no different than for least squares minimization, because all I'm saying is let's minimize for each data point the actual y minus the predicted y, and the predicted y is nothing but beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 goes on. So essentially j goes from 1 to p, meaning p is the total number of independent variables, n is the total number of data points. So you do it for each data point. You look at the deviation of the fitted value, the actual value to the estimate or the predicted value. And the goal is this deviation is what needs to be minimized. The square of this deviation needs to be minimized on an ordinary least squares regression. But in addition to that, what we do with the ridge regression is we do this optimization with a constraint, and the constraint, it can be written like this. The constraint is that it's subject to some beta. You take each beta, which is each coefficient, square it, and the sum of those squares should be less than some value s, right? And that value s is essentially it's not like you have a particular number in mind. What winds up happening is that you can rewrite this optimization by just not having this constraint, but essentially out here just adding a minus lambda and summation of beta j square. So this is kind of like, you might have come across this with like Lagrangian multipliers. Essentially, when you have a single constraint on the coefficients, you can just rewrite the objective function to have that constraint integrated into the thing, and essentially it's like solving just that minimization without the constraint. But essentially the solution to that is what will ensure that your betas themselves are stable and not taking really large values. Another way to achieve the same thing is, again, even with the lasso regression, this should not be ridge, this should be lasso. Right. So even with the lasso regression, what you see is the same thing. You have the same objective function, but now it's subject to the constraint that the sum of the betas is less than some value s. And again, out here you can just wind up rewriting your objective function, but out here rewriting it does not do you too much good, because you cannot do the same trick as with standard calculus with Lagrangian multipliers, where you have a beta square. When you have a mod beta, it just becomes computationally harder. But just like we saw in the simple regression case, if you've got an Excel sheet or a MATLAB, you can just do the optimization and put this in as a constraint. And as long as your optimization technique is good enough, you should be fine. You should be able to just redo it. Okay. I hope that gives you some idea of regularization techniques, and look forward to seeing you in the next class. Thank you.